this is Emmanuel, and in today's video we'll be talking about conduction heat transfer and its governing law, which is the Fourier's law of heat conduction. Please subscribe to my channel in order to get a notification whenever I upload a video like this. So first of all, what is heat conduction? This is the mode of energy transfer between solid brought into direct contact that have different temperatures, or within solid as a result of temperature difference, or with liquids or gases as a result of temperature difference without any appreciable movement of matter. So conduction can occur between liquids or solid, but the molecules and atoms in the liquid should not move. So we'll come to the governing principle of heat conduction, which is the Fourier's law. So in the 17th century, a guy named Joseph Fourier discovered an empirical correlation that governs heat transfer in a solid. So the formula is stated that the negative gradient of temperature and the time rate of heat transfer is proportional to the area at right angles of that gradient through which the heat flows. So this is the main formula for the law. So this is heat transfer. The formula is relating heat transfer to K, which is the thermal conductivity, and AX, which is the cross-sectional area in the direction of X, and dt dx, which is the temperature gradient. So K, the unit for K is watt. The unit for K is watts per meter squared Kelvin, or watts per meter squared degree Celsius. And also the gradient, the temperature gradient, is equated to cold temperature minus hot temperature divided by X. The X is the length or the thickness of the material. Then heat rate, the unit for heat rate is watts, and the unit for heat flux is watts per meter squared. Heat flux is equal to the heat rate divided by the surface area. So heat flux is simply heat rate divided by surface area. So sometimes the formula can be written in the integral form. So you bring the dx over here, and you integrate it by the temperature, and you integrate this one too by the distance. So this is it. And also we come to the heat flow profile. So this heat flow profile is telling us how heat flows from a hot temperature to a cold temperature, and we all know that heat flow from a hot temperature to a cold temperature. So if this is the length, this x side is the length of the material, and the heat over here is hot, so temperature T hot, the temperature over here is hot, and it's traveling linearly to a cold temperature. This is the profile for it, and this is also the formula for it. But this is a Fourier's formula. But someone will ask, why do we have a negative sign over here? So we know that Qx, which is the heat flow, flows in the direction of hot temperature to cold temperature, which is also in the direction of the x positive axis. So it means this Q is positive, meaning everything here should also be positive. But someone will ask, why is a negative sign over here? The negative sign is over here because the temperature gradient, which is dt dx, is moving in the opposite direction to the x axis, to the x positive axis. So you bring the negative sign over here to cancel out this negative sign. We all know neg is 4, so negative times negative will give you positive, meaning everything over here is positive. And another formula we have to know is the formula for heat flow. Heat flow is equal to driving potential difference divided by thermal resistance. So this is the formula, and the driving potential difference is the difference between temperature, is the temperature difference. So if that one is the temperature difference, then RT, which is the thermal resistance, is automatically equal to L, which is the length, divided by K, which is thermal conductivity, multiplied by AX, which is surface area. So in the next video, we'll be talking about convection heat transfer and its governing law, which is the Newton's law of cooling. Thank you for watching my video.